In this video, we're going to look at some double replacement reactions, and we're going to do one example of each type of double replacement reactions. So the notes we will label as double replacement reactions, and there are three ways that we will know that a double replacement reaction occurs. One is, did we get a precipitate, an insoluble product? Did we get water as our product? And finally, did we get a gas as our product? If we have any one of these three, we know a double replacement reaction took place. So what I'd like to do is I'd like to first do an example. Question number 89, question A from the book. Rubidium iodide reacting with silver nitrate. So rubidium is from column number 1. So I'm going to, for our first example, page 305 in the book, question number 89, letter A. And rubidium is in column 1A. So rubidium is a 1 plus. And iodine is in column 7A. It's a 1 minus, so it would be RBI. When we look up RBI on the solubility chart, rubidium is actually not listed on this chart that we have, but we're going to assume that it's an aqueous solution since it's one of the reactants. So we have rubidium iodide, and it's reacting with silver nitrate. Silver is a 1 plus, nitrate is a 1 minus, so it's AgNO3. When we look up AgNO3, Ag is here, NO3 is here. It is soluble. It is soluble, just like what we assumed this one to be. So soluble means it's aqueous. So now the positive from RB is going to go with the negative of the second. So it's a 1 plus and a 1 minus, so that's easy to put together. And then I'm going to hold off on putting anything right here yet. And then we've got the positive Ag with the minus I, so it's AgI. And if we look up AgI, Ag and I, it shows that it's insoluble. AgI is insoluble, so it forms a solid precipitate. So we would put an S here for a solid precipitate, which means this one must be, remember rubidium is not on my list here. We could look him up, but because the one is insoluble, that means this one must be soluble. RbNO3 must be an aqueous solution. So this is the complete equation. Now I'm going to look at the ionic equation. Well, the ionic equation takes each one of these that are aqueous and separates them into their individual ions. The reason that they're separated, aqueous means it separated them into their individual ions. So all of these that show aqueous, I'm writing as separate individual ions. And I'm going to run out of room here. NO3 minus, aqueous, and then but this insoluble solid precipitate does not become separated. It stays together as a solid. The ionic shows it as it is. If it's aqueous, it separates. If it's a solid precipitate, it does not. The net ionic is where we only show the ions that changed. So what we can do is look at the solid precipitate And that means these substances must have changed because they started as an ion and ended up as a solid precipitate. Notice the RB. RB here, both in its ion form. It never changed. Notice NO3, NO3, never change. These are called spectator ions because they never change. Spectator ions are not involved in the reaction. They started as ions, they ended as ions. They just floated around watching what took place in the chemical reaction. For the net ionic, it only shows the ions that changed. And typically, we write the positive ion first. It's not a requirement, but typically we do. So we end up with the net ionic as being this, Ag plus I minus in aqueous solutions, turning into AgI as a solid. This is an example of an insoluble precipitate being formed, a solid precipitate that's insoluble. That's the first type of double replacement reactions that exist. In the next example, we're going to be looking at page 306, 92A. And on this one, what we have is we have phosphoric acid plus rubidium hydroxide. And then we'll figure out what the products are from those two reactants. So for phosphoric acid is H3PO4. H3PO4. It is an aqueous solution. Rubidium is a 1+. Hydroxide, even though it ends in IDE, it is on the back side of the periodic table as an OH minus. So this is a 1+, PO4 is a 3 minus, a 1 plus and a 1 minus. So the plus goes with the minus and the plus goes with the minus. We can write this either way, but we have H with the OH, the 1 plus with the 1 minus. We can also write this as H2O. And we also have the 1 plus with the 3 minus. So when we write that, it has to be Rb3PO4. And the reason it's got to be Rb3PO4 is because each Rb is a 1 plus, but each PO4 is a 3 minus. So you need 3 Rbs. So this is an example of the second type of method that a double replacement can occur. We produced water. We produced H2O or HOH, a 1 plus and a 1 minus, a 1 plus and a 3 minus. But we need to balance the equation. There's 3 H's over here, so we put the 3 there, but that gives me 3 OH's, so I put a 3 there. That gives me 3 Rb's, 1 PO4, 1 PO4. It's all balanced now. So that's the second type of question, is water produced in the double replacement reaction? For our final example, example 3, what we're going to look at is HCl reacting with HCl in aqueous solution, reacting with Na2S. Na2S, also an aqueous solution. H is a 1 plus, Cl is a 1 minus, Na is a 1 plus, S is a 2 minus because it's in column 6A. So when we put these together, the 1 plus will go with the 2 minus, so it's got to be H2S. Now, H2S is one of those 3 gases that we're looking for from our previous video being formed. So we put a G at the end of that. There were 3 gases that we were looking for. One is carbon dioxide, One is hydrogen cyanide and one is hydrogen sulfide. And we analyzed those in that previous video. Our other substance is a 1 plus and a 1 minus NaCl that will remain in an aqueous solution. The way I know that is if I looked up NaCl, it shows that it's soluble, so it's an aqueous solution. I know that this is a gas because there were 3 gases that we talked about forming. One is carbon dioxide, one is hydrogen cyanide, and the other is H2S, hydrogen sulfide. Any of those gases being formed, we write it as a gas. We still need to balance this equation. There's 2 Na, so I need to put a 2 here, which gives me 2 Cl's, but I need to put a 2 here. And then that matches the 2 H's, 2 H's, and the 1 S. So here were 3 examples. One forming an insoluble precipitate, one forming the H2O, in this case we wrote it as HOH, and one forming a gas. 3 indicators that would allow us to know that a double replacement reaction took place. I hope this helps with double replacement reactions.